so we're on page 117 of the Math 20 Absolute Value workbook and looking at dividing radicals, part 1, so this is lesson 4. And so the key thing to note in this particular case, to simplify these expressions, is this very first piece here that we looked at the other day, which was saying that the square root of a over b can in fact be separated to the square root of a divided by the square root of b, and of course the radicands must be greater than or equal to 0, because we can still take the square root of 0, it is 0. However, since we cannot divide by 0, then the denominator b, in fact, has to be greater than 0. But otherwise, they are still elements of the real numbers, which means that, yeah, they could be possibly fractions as well, or decimals. But of course, the fact is that we can't necessarily simplify them further. If the square root of 7, for example, that's going to end up being irrational, but it is still real. So if we take a look at m times square root of a divided by n square root of b, what we know that we could do is we could essentially separate those to m over n and simplify that fraction, reduce that fraction, times root of a divided by root of b. So you can simplify radical with radical, provided that the index is the same, and then simplify coefficient with coefficient then as well. So another option to look at is as well simplifying into mixed radicals. Certainly your final form should be simplified as much as possible, and that's going to mean that we do not have any perfect square factors within the radicand if the index is 2, or perfect cube factors if our index is 3. And so the idea is that there's lots of ways to go through it, and you're going to pick the path that is easiest for you. The other piece that is going to come up shortly as well is we also ideally do not want to have a radical left in the denominator. And that is something that we want to look at when we're considering simplifying. So we'll talk about that a little bit later. So if I've got square root of 30 divided by the square root of 6, then because these are both index 2 square roots, then we can simply divide root 30 divided by root 6, and so that is just square root of 5. Easy as that. So in this particular case, we've got 8 over 2, which is simply 4. Here the index is is 3 for both, so cube root of 21 divided by cube root of 3 is simply going to be cube root of 7, so 4 times cube root of 7. For C, we've got a couple of things that we can do with this. So I know some people might consider simplifying square root of 48 first and expressing that as a mixed radical. Certainly you can, but if we can make the numbers smaller by first dividing these, then that's what I'm going to do. So I'm going to look at 15 over 10 and not change it to a decimal, but rather simplify that fraction. So 15 tenths, divide top and bottom by 5, and so we've got 3 halves, and root 48 divided by root 6 is going to be square root of 8. But then we know that square root of 8 has a perfect square factor of 4, so then we've got 3 root 4 times root 2, and that is all over 2, and so root 4 is the same as 2, so you could rewrite it if you wanted to, so you could say 3 times 2 root 2 all over 2, and so that's 6 root 2 divided by 2, or we could see that 2 over 2 is simply just going to be 1 over 1, so our final answer is just going to be 3 root 2 in that case. And for any of these, remember, you can always check using your calculator. You can take a look at your original expression, 15 root 48 divided by 10 root 6, and put that into the calculator, get a decimal approximation, and that will, of course, be the same, or should be the same, for the decimal approximation for 3 root 2. So in this particular case, for D, 4 over 12 is the same as 1 over 3, and the square root of AB divided by the square root of A is just going to be the square root of B. So we could leave it in a couple of ways. You could leave it like that if you'd like. If you want to put the coefficient out front and have 1/3 root B, that is totally fine. If you would like to simply write it as root B over 3, all three of these answers are totally acceptable. Okay. In some cases, then it says converting radical into simplest mixed radical form before dividing will make the calculation easier. So again, this is one of those scenarios where they're just trying to explain to you that you've got choices to make. And it's not to say that one is better than another. It's just nice to have options. So we should all end up at the same answer, the same final simplest form, but lots of ways to get there. So let's talk about what they're referring to. So if we take a look at root 54, well, what do we know is that root 54 has a perfect square factor of 9, so I could make that root 9 times root 6, and for root 8, we could make that root 4 times root 2, and then we're looking at 4 times, and root 9 is the same as 3, and just going to leave that root 6 divided by root 2 is the same as root 3, so that's me dealing with this portion right here, and then 3 root 4 is the same as 3 times 2. So really we're just looking at 12 root 3 over 6, and 12 over 6 is of course 2, so it is 2 root 3. So that's one way to get there. The other way, so doing something similar to what we did in class example number 1, would be to say, hey, the square root of 2, so if I looked at reducing root 54 and root 8, there's a common factor of 2 in here, and so we could say that this is the same as 4 over 3, and then root 27 over root 4 in that particular case, and then root 4 is simply 2, so we've got 3 times 2 in the denominator, and the numerator 4 times, and root 27 is the same as root 9 times root 3, and so then we've got 4 times 3 root 3 over 6, and that certainly looks familiar. That's what we've got right there. So you can see that we end up with exactly the same final answer, just a couple of different ways as to how to get there. And is one better than the other? It's totally up to you. It's hopefully about getting to smaller numbers. So if it is reducing things first, or between radical and radical, or simplifying those radicals into mixed radicals, totally up to you. Okay, so let's take a look for the second one. So in this particular case, if we simplified 8 root 126, then you might see that 126, 9 goes in. Some people might know that, and other people might not, in which case this method may not be the best way for you. So 9 times 14 is 126. So then in the denominator, then root 112. If we take 16 goes into that, so root 16 times root 7. So again, not everybody knows that off the top of their heads, so I'll give you another way to go through this as well. So then if we continue to follow this way though, 8 times root 9, so root 9 is the same as 3, and then root 14 over root 7 is the same as root 2, and root 16 is the same as 4. So then we've got 24 root 2 over 4, or if you wanted to, you could reduce ahead of time and say, hey, 8 over 4 is the same as 2 over 1. So really, we're talking about 2 times 3, or 6 root 2. So that would be your final answer in that case. So for those of you who didn't know that 9 times 14 was 126, or 16 times 7 was 112, so what might occur to you in this particular case maybe says, hey, you know what, I know that 2 goes into both 126 and 112. So if we simplify that, then I've got 8 root 63 over root 56. And that's kind of nicer because the numbers have gotten smaller in this particular case. And then again, we could see that root 7 goes into both of them. So if we divided them both by root 7, then I've got 8 root 9 over root 8. And then root 9 is the same as 3, so we've got 8 times 3 over, and root 8 is root 4 times root 2. So now we've got 24 over 2 root 2, and 24 over 2 is the same as 12. So we've got 12 over root 2. Now the issue with this is it's obviously not the same as 6 root 2, and so then the question is, okay, well, how is it then that I get that same answer, and why isn't it the same? Well, first thing, double check in your calculator that they are in fact the same decimal approximation. They are both equivalent to, let me just work that out for us, so 12 divided by 2, and so they should both come out to approximately 8.485, so the same decimal approximation there. And so what we need to do is something we call rationalizing the denominator. So we'll get into that a little bit more later, but the idea is that we don't like having a radical in our denominator. But if you recall, when we looked at multiplying radicals, what we know is that if I multiply two radicals that have the same index of 2 and with the same radicand, then what ends up happening is that we end up with just that radicand. So if I multiply by root 2 over root 2, because by multiplying the same top and bottom, it's like multiplying by 1, so the value doesn't change. And then root 2 times root 2 is root 4, and root 4 is, of course, just 2. So then we've got 12 root 2 over root 4, also known as 2. And 12 over 2 is, of course, 6. So then 6 root 2. So there we can see that we have exactly the same value. So the whole process of getting a radical out of the denominator is called rationalizing the denominator. Okay, let's take a look at this last question then. So 10 over 20 is, of course, 1/2, and the cube root of 162. So I'm looking at factors, or perfect cube factors of 162. I know that 81 times 2, so is 162, so that must mean that 27 goes in as well. So we can say then that this is the cube root of 27 times the cube root of 6, and then for 128 we're looking at perfect cube of 64, so cube root of 64 times the cube root of 2. And so cube root of 27 is simply 3, and cube root of 6 divided by cube root of 2 is cube root of 3. And then in the denominator we've got 2, and the cube root of 64 is going to be 4. So then we have 3 times the cube root of 3 over 8, and that is our final answer there. Excellent. So taking a look at class example number 3, so divide each term in the numerator by the denominator and simplify. And so this is, of course, based on dividing polynomials, right? So you know notice a lot of the things that we're doing are similar to working with polynomials and like terms. So you don't have to write this step out, but what it's actually saying is that this expression root 24 plus root 48 minus root 108 is the same as root 24 divided by root 6 plus root 48 divided by root 6 minus root 108 divided by root 6. And so certainly we know that we cannot add root 24 plus root 48 and subtract root 108 because they are not like radicals. We could certainly try to simplify and see if we end up with like radicals, but this is a much nicer way of starting things out anyways, because our numbers get smaller since they all divide by root 6. So we would have then square root of 4 plus the square root of 8 minus the square root of 18, I believe. And so then those radicals can be simplified further. So root 4 is the same as 2 plus, and root 8 is root 4 times root 2 minus root 18 is root 9 times root 2. So we're looking at 2 plus 2 root 2 minus 3 root 2, and 2 root 2 and negative 3 root 2 can be combined to make that 2 minus 1 root 2 then. So that 1, of course, as a coefficient is optional, or negative 1, I should say. So our answer, 2 minus root 2. Okay, so rationalizing the denominator. So again, it is the denominator cannot contain a radical, and the radicand itself cannot contain a fraction. And so the whole idea of rationalizing the denominator, where that came from, is the idea of, well, before the time of calculators, dividing 1 divided by root 13 was very difficult to do, and so the idea was if we could instead divide by an integer value, then it would be easier to do without the calculator. These days, it's to be honest, it's not as relevant because we have calculators available, but it is still a skill that we should know how to work with. So rationalizing the denominator, the whole thing again is the idea that, remember, if I take the square root of 2 times the square root of 2, that is the same as the square root of 4, which is of course 2. Square root of 7 times the square root of 7 is the square root of 49, which is of course just 7. So anytime I take the square root of x times the square root of x, it is just going to equal x. And of course, if I'm dealing with variables, we know then that x must be greater than or equal to 0 for this to be true then. So because of this, then, if I do not want the radical in the denominator, I know that I can multiply the bottom by root 13, and then that will give me 13, but if I'm doing that to the bottom, I have to do that to the top as well. So again, it's like multiplying by 1, so the value doesn't change even though the numbers are changing. So multiplying across the top, then we would have root 13 over 13. So 1 over root 13 is the same as root 13 over 13 with no radical in the denominator. In this case then, no radical wanted in the denominator, so I'm going to multiply the bottom by root 2, which means I need to multiply the top by root 2. Root 5 times root 2 is root 10, and that is divided by root 2 times root 2, which is 2. Do not be tempted to simplify that at all. It is already done, because we cannot simplify. We can only do radical with radical or whole number with whole number. Okay. In this particular case, then obviously we could start by multiplying by root 6 over root 6, but if we take a look at what we did previously, we know that that can actually be reduced, right? So root 2 over root 6 is really the same as root 1 over root 3. So root 1 is, of course, just 1, and so it's 1 over root 3. And then to rationalize, I need to multiply top and bottom by the square root of 3, and so then we've got root 3 over 3, and that negative, I'm just going to move that negative into the numerator. So just because typically we don't want to leave a negative in the denominator, we'll either put it out front or up top. Then there's no need to multiply by negative root 3 over negative root 3. You can, but not needed, because the whole idea is just to get rid of the radical. In this particular case, then, we're multiplying top and bottom by root 3 and root 3 again. So then I've got square root of 60 over 3, and even though we think we're done, we're not, because there is a perfect square factor in 60, and that is 4. So we could have simplified that earlier, of course, as well. So that's the same as root 4 times root 15 over 3, and so then we are looking at 2 root 15 over 3, and that is our simplified form. Okay, for class example number 5 then, so we've got 7 over 3 root 7, and so I see a lot of people who multiply top and bottom by 3 root 7, and it's not that it's wrong, it's a question of, do you need to multiply by 3 root 7? What is the smallest thing that you need to multiply by, just to keep our numbers smaller? And so, you know what, let's just try. What happens if we just multiply by root 7? So in the numerator, I would have 7 root 7. The denominator, I've got 3 times root 7 times root 7, and root 7 times root 7 is just 7. So we've got 3 times 7 then, or 21, and the 7 over 7 is just equal to 1, so our final answer then is root 7 over 3. Okay, for B, again, we can separate those out, remembering that we could look at that as root 18 over root 5. So to start, we could multiply top and bottom by root 5, but again, the numbers are getting larger, so if it helps you, then I would suggest actually simplifying that root 18 first. So root 18 is the same as root 9 over root 2 times root 5, and so then that is the same as 3 root 2 over root 5, and then we'll multiply top and bottom by root 5 over root 5 to give us 3 root 10 over 5, and that is our simplified answer with a rational denominator. Okay, for C, then again, I see a lot of people just jumping right in to rationalize, and they multiply by root 72 over root 72. Again, that's not incorrect. However, I personally don't know what root 72 times root 12 is, and so to avoid having to work with larger numbers, I like to simplify first, and so options to simplify, certainly you could change both of these radicals into mixed radicals, but I actually like to take a look at root 12 and root 72 and say, you know what, that reduces, because 12 goes into 72 6 times, so that's the same as 3 root 1 over root 6. So much easier. And now multiply top and bottom by root 6, so then we have 3 root 6 over 6, and 3 over 6 is the same as 1/2, and so then we've got root 6 over 2. Awesome. Okay, if you take a look at class example number 6, so it says simplify the radical expression by rationalizing the denominator first, or dividing numerator and denominator by root 2. And so if we take a look at this then, so rationalizing the denominator first would mean that I've got 3 root 18 minus root 12 divided by root 2. So rationalizing would mean that I need to multiply the top and bottom by root 2, which means that I would need to distribute that root 2 in. So then we've got 3 root 36 minus root 24, because we've essentially got distributive property here, and that is all over root 2 times root 2, which is just 2, and then 3 times 6 minus, and root 24 is the same as root 4. Whoops, that would be root 4 times root 6, and that is all divided by 2. And so we're looking at 18 minus 2 root 6 divided by 2. And so to simplify that, we need to divide both terms by 2, which is then 9 minus root 6 then. Okay. Alternatively, if we did that whole idea of dividing a polynomial by a monomial, it's the same as dividing each term by that monomial. So 3 root 18 minus root 12 divided by root 2 is like saying 3 root 18 divided by root 2 minus root 12 divided by root 2. So then we're looking at 3 root 9 minus root 6, and root 9 is just 3, so 3 times 3 minus root 6, and we get 9 minus root 6. So same answer, and 2 different ways of getting there. So consider which method you like better, and it might be a matter of what occurs to you at the time. It might be a matter of the numbers that you happen to be given as to what's going to work out nicely for us. Obviously, because both 18 and 12 are divisible by 2, that works out nicely. If it was 18, if you were, instead of dividing by root 2, maybe it was divided by root 7, then that's not going to work out nicely for us, in which case our only option would be to rationalize the denominator first. Okay, please let me know if you have any particular questions. Otherwise, we'll move on to the next lesson. Thank you.